Hello and welcome to the course Design and Analysis of Algorithms. Today we will study the Master Theorem and see how the recurrences can be solved using the Master method. Master method is a method for solving recurrences of the form T of n is equal to a T of n by b plus f of n, also known as the master recurrence, where a and b are constants and f of n is an asymptotically positive function. B should be strictly greater than 1. A should be greater or equal to 1. The master method requires memorization of three cases, after which the solution of many recurrences of this form can be solved quite easily with very little work. Before we dig into the master method, let's solve the master recurrence using the recursion tree method to see what is going on and how the master method works. In this case, we assume n is the exact power of b. In the first step, we will draw the recursion tree of the master recurrence. F of n is the non-recursive part and we will have a children in each step for each interior node. To solve for t of n, we need to find t of n by b. So we plug in n by b in the original recurrence equation and expand the tree. To find the value of t of n by b square, we plug in n by b square in the original recurrence equation and further expand the tree. The problem size is reduced to 1 at the kth level. To figure out the total cost, we will first find the leaf cost. For that, we need to find the value of k. Here, n will be equal to b to the power of k. Take log of base b on both sides and we get k equal to log base b of n. That is the height of the tree. Since a number of children are spawning at each interior node, at kth level, the number of leaves will be a to the power of k. We plug in the value of k and we get n to the power of log base b of a, which will be our leaf cost. Now we will find the interior node cost. At the root level, the cost is f of n. At the first level, the cost will be a f of n by b. At the second level, the cost will be a square f of n by b square, and so on until the k minus 1 level. So our total cost will be n log base b of a plus summation of from k0 to log base b of n minus 1 of ak f of n by bk. The summation sign represents summing up the cost at each level of interior nodes. Before applying the master method to solve some examples, let's try to understand how it is developed. There are three possible cases. The cost increases geometrically from the root to the leaves. The cost decreases geometrically from the root to the leaves, or the cost is approximately the same on each level. So the idea here is to compare f of n with n log b of a, which is the cost of the leaf nodes. In the first case, the cost increases geometrically from the root to the leaves. In this case, n log b of a should be asymptotically larger in growth than f of n by some polynomial factor of n to the power of epsilon. If this is the case, then the solution to the problem will be t of n is equal to big theta of n log b of a, as the most of the cost is coming from the leaf nodes. In the second case, the cost is approximately the same on each level. So there are total of log base b of n levels. The growth of n log base b of a is asymptotically equal to f of n. This means that the cost of each level will be n log base b of a, and there are total of log base b of n levels. So the final solution will be t of n is equal to theta and log base b of a log base b of n. In the third case, the cost decreases geometrically from the root to the leaves. So n log base b of a should be asymptotically smaller in growth than f of n by some polynomial factor n to the power of epsilon. In this case, f of n is the major factor contributing to the total cost. So the final solution will be T of n is equal to theta of f of n. The master method depends on the master theorem, which states that let a and b be constants. A should be greater or equal to 1 and b should be strictly greater than 1, and let f of n be a function, and let t of n be defined on a non-negative integer by the recurrence t of n equal to a t of n by b plus f of n. Then t of n can be bounded asymptotically as follows. If f of n is big O of n to the power of log base b of a minus some constant epsilon greater than 0, then t of n is theta of n log base b of a. This is the case 1 we discussed in the last slide, where the growth of f of n is asymptotically smaller than n log base b of a. If f of n is equal to theta of n log base b of a, which means if the growth of f of n is same as n log base b of a, then t of n is equal to theta of n to the power of log base b of a log n. This is the case 2 we discussed in the last slide, where the cost is equally divided amongst all levels of the tree. If f of n is big omega of n log base b of a plus some constant epsilon greater than 0, and if a of f of n by b is less than or equal to c f of n for some constant c less than 1 and all sufficiently large n, then we can say t of n is theta of f of n. This is the case 3, where the growth of f of n is greater than n to the power of log base b of a. In the third case, we also have to satisfy the regularity condition. This implies that the cost of each level should be strictly less than the cost of the level above it. Before we solve some examples using the master method, let us see the proof of the three cases of the master theorem. In the first case, n log base b of a is asymptotically growing faster by a factor of n to the power of epsilon as compared to f of n. If we solve this, we come up with n to the power of log base b of a divided by f of n greater than or equal to c times n to the power of epsilon. If we take f of n to the left hand side and the remaining to the right hand side and solve for this, we will end up with f of n is equal to big O of n to the power of log base b of a minus epsilon, which was the first condition of the case 1 of Master Theorem. Now coming back to the equation that we derived using the recursion tree method, let's prove case 1. Suppose f of n is n to the power of delta, where delta is strictly less than log base b of a. For this condition to hold, or b to the power of delta is less than a, then we will have the following equation. Here we are plugging in n over b to the power of k here in f of n, and we get n to the power of delta divided by b to the power of delta to the power of k. If we solve it further, we can see that this is a geometric series And since a is greater than b to the power of delta, we will use the following geometric series formula. The actual formula is x to the power of n plus 1 minus 1 over x minus 1. Here we have log base b of n minus 1. So we plus 1 to this, we will get log base b of n. We further solve this and we will get the following equation, where a over b to the power of delta minus 1 is a constant, so we replace it by some constant c. We multiply n to the power of delta and we get the following equation. Since delta is smaller than log base b of a here, the big O of this equation would be n to the power of log base b of a. And since the positive term is being added to n to the power of log base b of a, the big omega will also be n to the power of log base b of a. And hence, for this equation, the big theta will be n to the power of log base b of a. So we prove that if f of n is big O of n to the power of log base b of a minus some positive constant epsilon, then t of n is theta of n to the power of log base b of a. So now let us look at the proof of case 2, where the growth of f of n is equal to that of n to the power of log base b of a. We look at our equation that we derived from the recurrence equation, and we suppose that f of n is equal to n to the power of delta, where delta is equal to log base b of a, so that this condition can hold, or b to the power of delta is equal to a. So let's plug in n to the power of delta into the above equation and we get the following equation. Since a is equal to b to the power of delta, this term will become 1 to the power of k, which is just 1. So we get the following equation. Now n to the power of delta is being added log base b of n times. That is from 0 to log base b of n minus 1. So we have n log base b of a plus n to the power of delta log base b of n. We plug in the value of delta here and we get the following equation. And by using the property of changing the base of log, we can change the log base b to log base 2 of n, and our big theta in this case will be n to the power of log base b of a log n. Here the c represent some constant when the base of the log is changed. We have proved case 2 that if f of n is theta of n to the power of log base b of a, then t of n is equal to theta of n to the power of log base b of a log n. Now let us see the proof of case 3 of the Master Theorem, where the growth of f of n is asymptotically greater than n to the power of log base b of a. We use the recurrence equation we derived from previous slides, and we suppose that f of n is equal to n to the power of delta, where delta in this case will be greater than log base b of a, so that this condition holds, or b to the power of delta would be greater than a. If we plug in the value of n to the power of delta into the equation, we will get the following equation. We can see a geometric series here, and since b to the power of delta is greater than a, this will be less than 1. So we will use the geometric series formula of 1 over 1 minus x, and we get the following equation. And since this whole part here is a positive constant, we just replace that by a positive constant c. And now, since delta is greater than log base b of a, our this term of n to the power of delta will be greater than n to the power of log base b of a. Hence, we will have theta of f of n. Here f of n is equal to n to the power of delta. So we have proved case 3 that if f of n is big omega of n to the power of log base b of a plus some positive constant epsilon, and if a f of n by b is less than cf of n for some constant c less than 1 and all sufficiently large n, then t of n is big theta of f of n. It is important to note that the three cases do not cover all the possibilities. There is a gap between case 1 and case 2 when f of n is smaller than n to the power of log base b of a but not polynomially smaller. And there is a gap between case 2 and case 3 when f of n is larger than n to the power of log base b of a but not polynomially larger. If f of n falls into one of these gaps, or if the regularity condition in case 3 fails to hold, the master method cannot be used to solve the recurrence. Now let us solve some examples using the master method. First, we will solve the following recurrence of merge sort and quick sort through master method. If we map this recurrence equation to the master recurrence, we have a equal to 2 from here, b equal to 2 from here, f of n equal to n from here. Now we have to compute n to the power of log base b of a. We plug in a and b and we have n to the power of log base 2 of 2. So log base 2 of 2 is 1. So n to the power of log base b of a becomes n. Now in the next step we will compare f of n with n to the power of log base b of a. In this example, both of them are same here, and here the power of n is same, so the case 2 will be applied. Hence, t of n is theta of n log of n. Now let's look at another recurrence. Here a and b will be 2, f of n will be n square. We need to compute n to the power of log base b of a, which will be n in this case. In the next step we will compare f of n to n to the power of log base b of a. We can see that the power of n in f of n is greater than n log base b of a. So the growth of f of n is greater than n to the power of log base b of a. So case 3 is applied. Before that, we will verify the regularity condition. We plug in the value of a and b. We have to find f of n by 2. So we plug in n by 2 into f of n and we get the following, and we solve and we get the value of c less than equal to half. For the regularity condition to hold, the c should be less than 1, which is true in this case. So case 3 is applied, which states that T of n is theta of f of n. So in this case, it will be theta of n square. Hence, for this recurrence equation, T of n is equal to theta of n square. Let's solve the following recurrence using the master method. For this problem, A will be 9, B will be 3, f of n will be n to the power of log base b of A will be n square. In the next step, we will compare f of n and n to the power of log base b of A. We can see that n to the power of log base b of A is n square, while f of n is n. So the growth of n to the power of log base b of A is greater than f of n. So case 1 is applied. For case 1, T of n is theta of n to the power of log base b of A, which we have computed to be n square. Hence, for this recurrence equation, the solution is T of n is equal to theta of n square. Let's solve the recurrence of binary search using master method. In this case, A will be 1, B will be 2. Since f of n is 1, that is equal to n to the power of 0. We compute n to the power of log base b of A. Log base anything of 1 is 0. So in this case, n to the power of log base b of A will also be n to the power of 0. In the next step, we will compare f of n and n to the power of log base b of A, which in this case are equal. So case 2 is applied. For case 2, T of n is equal to theta of n to the power of log base b of A log of n. We plug in the value and we get log n as the solution. So the final solution for binary search recurrence equation will be T of n is equal to theta of log n. For this recurrence equation, A will be 4, B will be 2, f of n will be n cube, n to the power of log base b of A will be n square. So we compare f of n and n to the power of log base b of A. Here f of n has a power of n equal to 3 and n to the power of log base b of A has n square. So the growth of f of n is greater than n to the power of log base b of A. So case 3 is applied. So we will verify the regularity condition. We plug in the value of A and B and we plug in n by 2 in f of n and we get the following, and we solve for C. So our C in this case is less than equal to half, which is less than 1. So case 3 is applied. So our T of n will be theta of f of n, which is in this case will be n cube. So for this recurrence equation, our solution is T of n is equal to theta of n cube. For the following recurrence, A will be 1, B will be 2, f of n will be n square, n to the power of log base b of A will be n to the power of 0. So we compare f of n with n to the power of log base b of A. We can see that the growth of f of n is asymptotically greater than the growth of n to the power of log base b of A. So case 3 is applied. We will check the regularity condition. So in this case, C turns out to be less than 1 over 4. So case 3 is applied. So T of n will be theta of f of n. So for this recurrence equation, the solution is T of n is theta of n square. For this example, A will be 4, B will be 2, f of n will be n square. N to the power of log base b of a will be n square. So if we compare f of n with n to the power of log base b of a, the growth of both of them are equal. So case 2 will be applied. So t of n is equal to theta of n to the power of log base b of a log n. So the solution to the following recurrence equation will be theta of n square log n. For this example recurrence, a will be 7, b will be 3, f of n will be n square. So if we compute n to the power of log base b of a, that is around n to the power of 1.77. So if we compare f of n with n to the power of log base b of a, the growth of f of n is greater than n to the power of log base b of a. Hence, case 3 is applied. For that, we need to check the regularity condition. C turns out to be 7 over 9, which is less than 1. So case 3 will be applied. T of n will be theta of fn, and for this recurrence, the solution will be T of n is theta of n square. For this example recurrence, a will be 7, b will be 2, f of n will be n square, n to the power of log base b of a will be approximately equal to n to the power of 2.81. If we compare f of n with n to the power of log base b of a, it turns out that n to the power of log base b of a is asymptotically growing faster than f of n. Hence, case 1 will be applied. So T of n will be theta of n to the power of log base b of a. So the solution to this recurrence will be theta of n to the power of log base 2 of 7 or n to the power of 2.81. For this recurrence, a and b will be equal to 2. The square root of n is n to the power of 1 by 2 or half. So f of n will be n to the power of half. N to the power of log base b of a turns out to be n. So if we compare f of n with n to the power of log base b of a, the growth of n to the power of log base b of a is faster than f of n. So case 1 is applied. T of n is theta of n to the power of log base b of a. So for this recurrence equation, the solution is T of n is equal to theta of n. Now let's solve this interesting problem using Master Theorem. In this case, a will be 3, b will be 4, f of n will be n log n, n to the power of log base b of a will be n to the power of 0.79. If we compare f of n and n to the power of log base b of a, we can see that f of n has a higher growth than n to the power of log base b of a, because the power of n here is 1 as compared to here, which is 0.79. So case 3 will be applied. So now let's look at the regularity condition. If we solve for c, we get c is less than equal to 3 by 4, which is less than 1. So case 3 is applied. So our T of n will be theta of f of n. So the solution for this recurrence equation will be n log n. Now let's try to solve this tricky recurrence equation using master method. In this case, a will be 4, b will be 2, f of n will be n to the n square by log n, n to the power log base b of a will be n square. Now if we try to compare f of n and n to the power of log base b of a, we figure out that there is a non-polynomial difference between f of n and n log b of a. So master method does not apply. The difference must be polynomially larger by a factor of n to the power of epsilon, where epsilon is greater than 0. In this case, the difference is only larger by a factor of 1 over log n. So, master method does not apply to this recurrence equation. Now let's look at another tricky recurrence equation. In this case, a is equal to 2, b is equal to 2, and f of n is equal to n log n. N to the power of log base b of a turns out to be n. If we compare f of n with n to the power of log base b of a, it seems that case 3 should apply because the growth of f of n is n log n, which is greater than the growth of n to the power of log base b of a, which is n. However, there is a non-polynomial difference between f of n and n to the power of log base b of a, hence master method does not apply in this case. The difference must be polynomially larger by a factor of n to the power of epsilon, where epsilon is greater than 0. In this case, the difference is only larger by a factor of log n. So, for this recurrence equation, the master's method does not apply. Here are some practice questions that you can solve at home. So solve the following recurrences using the master method. I hope you have enjoyed the video and have learned how to apply master method to solve recurrences. Thank you and have a nice day.